This video is about Gibbs Free Energy, or the energy that tells you if the reaction is be favorable. You should already be able to define enthalpy and entropy, which are the things that tell you if it's going to be favorable or not, and then describe what Gibbs Free Energy is, how it's measured, and compare samples, and calculate it using formations, Hess's law, a new set of formulas. So lots and lots of math. So just like any other enthalpies or entropies of formation, Gibbs can also be found by doing products minus reactants. This number can tell you if a reaction is spontaneous or not at a given temperature. So if the Gibbs is a negative number, it is spontaneous, so that means it's releasing energy as it works, and so it is working. And if the Gibbs is positive, it's not spontaneous, it requires energy in order for it to work. So here you see the little monkey sleeping. He's not working, so he is going to be a positive Gibbs energy, right? So Gibbs Free Energy formation example, if you're given, this is the same exact problem we've been given for heat and entropy when we're just doing it for Gibbs. It'll be 3 CO2, so 3 times negative 394.4, and 4 water, so 4 times negative 237.13, minus the reactants, which are C3H8. Notice that it's negative 23.47, and there's only one of them. And once again, just like heat, Gibbs and heat are very similar. The oxygen is going to be 0 because it's a pure element at 298 Kelvin and 1 atmosphere. So you're going to put a 0 in. If it's not given, you can probably assume it's 0 or you're solving for it. This gave us a negative value of 2,108.3 joules per mole. Remember, when you're adding and subtracting, to go by decimal places. Since one of them only gave me 1 decimal, I have 1 decimal. It looks like a lot of sig figs, but remember, it's only actually 1 decimal sig figs. In that case, from here, something that we should notice is the units. Oh, I did a bad job of copying. The units should be kilojoules per mole, copying from the table given, which is similar to the heat values. Heat values are also kilojoules per mole. Remember that entropy, the weirdo one, is not. Entropy is joules per mole Kelvin, and therefore we'll have to do some finessing with those units. Also, entropy was not 0, so entropy is the odd particle out there, here, odd thing. So again, elements are 0, the units are kilojoules per mole, and this only tells us if the reaction is favorable and spontaneous at this temperature. There's other ways to calculate the Gibbs at different temperatures. So if we recall from previous lessons, if you know the heat from a lesson or the entropy of a lesson, you can find the Gibbs. So this was all the 3 values we had from the last 2 videos and this video. There is a formula that is delta G equals delta H minus T delta S. It's on your reference table. And if we plug the numbers in, the H could be negative 2220.0 kilojoules. We're going to subtract the temperature that has happened because they had degree symbols. These temperatures are 298 Kelvin. And then we're going to put our S value in, but we'll notice that the S value is not in kilojoules. So when I converted it to put in my calculation, I changed the S value to kilojoules. That way it matches the kilojoules in Gibbs. Everything should be kilojoules. So I divide the S by 1,000 to do the calculation. Really important, write in your notes. And then multiply and subtract. And I get a value of negative 2,108.4. Hey, that is essentially what we did by getting products minus reactants. So Gibbs is tied to how much heat is either required or given off, and how much entropy is either getting more ordered or less ordered, right? And so you can use this calculation to find Gibbs. Notice the S, again, had to be modified for units, so make sure you double do that, because the reason for that is the temperature is also associated with the entropy. The higher it is, the higher the entropy. The lower the temperature is, the lower the entropy. And that value, 298, makes that S value a lot bigger and competes with the heat. So generally, this is our table, and I would pause the video and write something like this down. That if the heat is negative and exothermic, that is spontaneous, or most times, and S, if it's increasing in randomness, then it's also good, and that's because we're going to be multiplying it by a negative temperature, which actually makes that negative. A negative and negative means Gibbs has to be negative and spontaneous at all temperatures. For example, it is spontaneous for ozone to turn into oxygen at any temperature. If the opposite is true, the positive endothermic is not very spontaneous, and entropy being negative means it's more ordered. That's also not, because when we multiply by a negative temperature value, it also becomes positive. 2 positives means Gibbs has to be positive, and it's never spontaneous. So if ozone spontaneously turns into oxygen at all temperatures, that means oxygen can never turn into ozone spontaneously. We require energy and require order. Then we have these random ones here that are a mixture. If the heat is negative, that's good, but the entropy is also getting ordered, that's bad. There could be competing factors, because if you negate the T, that becomes a negative H but a positive S. How will you know if the Gibbs will be positive because the entropy is high, or negative because exothermic, right? So we want to see if this would be spontaneous at low temperatures because that makes minus T delta S a smaller factor, and then non-spontaneous at high because that would make the minus T delta S a bigger factor, which makes Gibbs positive. An example of that would be water liquid turning to solid. This only happens, water only freezes if it's cold, right? So that's spontaneous if it's cold at low temperatures because we're getting more ordered, right? So therefore you need to put energy out to do that. In the next example, the opposite from the previous. If the heat is in, endothermic, that is a problem because that is not particularly favorable. And then, but in the case of entropy, it is increasing in entropy, so that is favorable. And when I multiply by minus T, that becomes a negative value. So now we again have competing factors of heat and entropy, and it could be positive or negative depending on how big the T is. This time it's spontaneous at high T's and non-spontaneous at low. For example, water solid becoming liquid only happens if it's putting in energy, endothermic, because it is becoming more random, right? So these are competing factors. It's important you know that. One of the ways that I always thought of it is that I just look at the T value, and that will either make the S more favorable or less favorable. And so that's where we get high and low T examples from. Under any conditions, like 298 when atmospheres are standard conditions, or not standard conditions, if you don't have standard conditions, you can fix it using a delta G at any condition is equal to delta G at the standard condition, notice the little degree sign, plus R, T, L, and Q. Finally, we get to talk about the R that is not 0821. The R that we're talking about here is the 8.314 value that's in joules per mole Kelvin. And then ln of Q is a natural log of the products over reactants. The reason it's not ln of K is because K would have been at standard conditions. Q is in when you're not really sure if that's equilibrium. And then you would just plug numbers in and decide if you know you have a spontaneous or non-spontaneous reaction. For example, calculate the Gibbs free energy of a Haber process at 273 Kelvin. Notice it's not 298, it's cold. If these are the values and the Gibbs is given for ammonia at negative 33 kilojoules per mole if it's standard. So what we're going to do is use that formula I just showed you. The standard is negative 33. The R is 8.314 from your reference table. The temperature was given in the question at 273 Kelvin. Make sure it's Kelvin. And the natural log is the products of this reaction, ammonia, squared, because there's going to be 2 ammonias every time you make it. Maybe write your reaction out. 3 H's plus 1 N is 2 NH3s. So then your H's are 1, and then you need 3 of them to balance, and 0.05 is your nitrogens. So this is your products or reactants if you write a balanced equation for making ammonia. When you plug it all into your calculator, I would recommend going backwards. Natural log this value, multiply by 8.34, and then add a negative 33,000 to it because it's easier. My final answer was sig figs and appropriate units I put into kilojoules per mole. Notice that this was 8.314 was in joules. So I changed this one to joules as well. But you could have instead, and then I changed it back to kilojoules. That was probably stupid. What you could have done instead is kept it negative 33 and changed this 8.314 to kilojoules, so 0.008314, and then you would have stayed in kilojoules the whole time. But the point is that 8.314 is in joules. The number that was given is in kilojoules, so you got to change it around a little bit so that they're the same unit. And my final answer was negative 24.36. So it was saying that at 298 Kelvin, remember standard, it was particularly spontaneous, negative 33. And if I cool it down to 273, it was a little less spontaneous. So this reaction works when it's hot. So just notes about the units that you should write down. So again, at equilibrium, Q is K, right? And the G will be 0 because at equilibrium it's both going forward and reverse. Neither one is more spontaneous than the other. And so then if you know that Q is K, so plug it in for K, and G is 0, you can rearrange the formula to make it G equals negative RTL and K. So this is for if it is at equilibrium in standard state, you can get Gibbs from K or K from Gibbs. Equilibrium from spontaneity. So this equation is also in your reference table. And how they're related is recall that if K is more than 1, it's product favored. That means it's going forward. And if K is less than 1, it's reactant favored. It's going reverse. That also works with Gibbs. If Gibbs was less than 1 or negative, the reaction was spontaneous and going forward. And if the Gibbs was more than 1 or positive, the reaction is spontaneous in reverse reaction because it's not spontaneous going forward. That means these are telling you the same thing. All in all, Gibbs and K are related. If Gibbs is negative, K has to be over 1. And if Gibbs is positive, K has to be less than 1. Since it's in red, I would suggest writing that down. So if K is 1, what is Gibbs it, and what does that mean? Again, K can only be higher than 1 or less than 1. That's its pinnacle, its turning point. Gibbs is either negative or positive, so its turning point is 0. Gibbs would be 0, that's how we got the formula. So how do we use that formula? It says the value of the equilibrium constant of a reaction is 45, so K is 45 at 298 Kelvin. And at the same temperature, the reaction is not at equilibrium has a Q value of 35. What we want to know is determine the Gibbs value and show that the value Gibbs tells you the same reaction forward or reverse as Q states. Q saying at 35 versus K at 45 is saying the reaction should continue to go forward, right? But we're going to see if Gibbs tells us the same thing, which it should. So we're going to calculate a Gibbs for the reaction at negative 8.314 from the reference table, temperature 298, ln of K 45, we get a value of negative 9.43. That means it's spontaneous at normal temperatures. And if we do it again for the non-spontaneous, we take that number and we put it to joules. That's how I always do it. 8.314 is already joules. 1098 is Kelvin temperature because that's what they said. And then the ln of Q, 35. And we get negative 620 kilojoules when I change it to kilojoules. And we put it in joules and change it back again like I did before. You can keep the whole thing in kilojoules if you prefer. That would mean that you would have 0.008314 over here. What it's showing you is that at the Q, it's even more spontaneous. So that means it is going forward, just like the K said. So if G is negative, which is spontaneous, it favors a forward reaction even more than the original reaction. One last thing, both Gibbs and free energy and entropy can be calculated using Hess's law, just like enthalpy was. So we were saying if you were given questions where diamond is rusting and graphite is rusting or burning in oxygen, and these are the values, you can figure out how much energy or how spontaneous it is to make diamond go to graphite. So all you would have to do is reverse the second equation, so graphite's on the other side. That means the oxygens and the CO2s will cancel out, so I just reversed it and rewrote it. And when you sum the Gibbs, it comes out to be negative 3, which means that it is somewhat spontaneous for diamonds to turn into graphite. How sad. But why don't we see that happen? The reason we don't see that happen in real life, diamonds turning into graphite, is because it actually has a really high activation energy. It requires a lot of energy to do it. It might have particles that don't have the proper energy and orientation to do it, or the proper energy to do it. So although it is spontaneous reaction at standard state, it's just a very slow process. So at this point, you should be able to describe what Gibbs free energy is, how it's measured, and compare samples using all the different types of calculations.